Hello, you're welcome. All right, so we are looking at the equilibrium of forces. So when a system of forces said to be in equilibrium, all right, system of coplanar forces is said to be in equilibrium. Okay, when their resultant, when the resultant of all the forces acting on that plane is equal to zero. Okay, so when the resultant of system of forces acting on the plane is equal to zero, such system of forces is said to be in equilibrium. All right. Now we're going to list out the condition for system of coplanar forces to be in equilibrium. Now, before I actually list out the conditions, okay, apart from the one I've actually stated, the question is what's a coplanar force? Now, a coplanar force, okay, is actually a system of forces that is acting on the plane at the same time. So they are called coplanar force. Let's say you have a plane like a beam, then you have forces, okay, F1, F2, and F3 acting on this beam at the same time. Okay, let's say this F1, F2, F3 is acting downward, is pushing the beam downward. Let's say that I have another force, okay, pushing the beam upward, F4. Now, if these forces are acting on this beam, on this plane at the same time, they are called coplanar force. Now, if the resultant force, okay, resultant of all these forces on this plane is equal to zero, then uh this forces is said to be in equilibrium. Okay, and uh at the point where the resultant of all these forces, their algebraic sum is equal to zero, okay, then you notice that this beam will be at rest. It will not move. Why? Because the forces is actually equal to zero. The resultant of the forces is equal to zero, so there won't be any motion. Remember, what actually leads to motion is force. So a situation where force is equal to zero, then definitely there won't be any acceleration. Acceleration also will be equal to zero. So now let's now look at the condition for coplanar forces to be at equilibrium. So we've already stated the, okay, one of it. We said that the sum of the forces, or the sum of the forces acting on that plane, or the resultant of all the forces acting on the plane, must is equal to zero. Number two, and that condition is, okay, the algebraic sum of the force acting in one direction, okay, acting in one direction, let's say in x direction, is actually equal to the algebraic sum of the forces acting in the opposite direction, okay, let's say opposite x direction. So invariably now, and the same thing happens if we are dealing with y, algebraic sum of the forces acting in the vertical direction should be upward, acting upward, should be equal to the algebraic sum of the forces acting downward. This is another condition. So the algebraic sum of the forces acting in one direction should be equal to the algebraic sum of the forces acting in opposite direction. So for me to illustrate that, let's say I have a vertical axis and of course a horizontal axis. Okay. So of course, you know very well that I can use arrow to show that this is positive x, then this is negative x. This is upward, which is positive y, and this is downward, this is negative y. So if this system is at equilibrium, that simply means that the sum of the forces acting in the positive x should be equal to the sum of the forces acting in the negative x. The sum of the forces acting upward should be equal to the sum of the forces acting downward. Okay, so that is one condition. Then of course another condition is that the forces must be concurrent. Okay, the forces must be concurrent. Concurrent in the sense that they must be acting on that particular body at the same time. Okay, they are not acting sequentially. For that particular body to be at equilibrium, all right, the forces acting on it, okay, must act on it at the same time. Those forces must be concurrent. Because if they're acting sequentially, this body won't be at equilibrium. Let's look at a situation where the downward force we wait until the upper force will wait until the downward force finish acting on this body. Then you know very well that this body will move, okay, before it comes to rest, and that is not equilibrium. So the forces must be concurrent. All right, then of course the last but not the least condition is that the algebraic sum of clockwise moment, the algebraic sum of the clockwise moment, okay, about any point on that particular object, okay, is should be equal to is equal to the algebraic sum. It's equal to the algebraic sum of the anti-clockwise moment, sum of the anti-clockwise moment. So now this particular last condition, okay, is the principle of moment which we are going to study. That's going to be our next subtopic. Okay, so we're going to study the moment of a force. So I will actually explain this last condition. Okay, let's actually look at the moment of a force. Moment of a force. All right. Now, what is moment of a force? Now, moment of a force in a very simple definition. Okay, moment of a force in a very simple definition is the turning effect, the turning effect of a force. Of course, you know very well that according to Newton's, okay, every if you apply a force will either push or pull an object, and once that push or pull is being okay applied, the motion is what you see. Motion is is the end product of the application of a force. And the question is, this motion, of course, you know, motion is of different types. So if the force that is applied actually causes the body, okay, that is receiving the force to turn, or it actually creates a turning effect, such turning effect is what we know as moment. For example, okay, let's look at the handle of a door. Okay, so you want to open the door. By the time you apply the force on the handle of that door, what happened? The handle actually turns. All right, it actually rotates. So such turning effect is what we refer to as moment. But mathematically, we actually define moment, okay, in a different way. So mathematically, this is another way of defining moment. The moment of a force is defined as the product of the force. Okay, of course, the moment of a force is always about a point. So look at the way I define the moment of a force about a point is defined as the product of the force and the perpendicular distance. So this is a symbol of perpendicular distance. Okay, from uh about a point, okay, from the point of action. All right. So if I want to illustrate this, okay, this moment, okay, moment being equal to force times perpendicular distance, right? If I want to illustrate this, I will actually use the best way to illustrate moment of a force is the experiment we conduct in the laboratory, okay, on experiment on pivoted meter rule, okay. So a meter rule is actually pivoted at a point. If the point where this meter rule is being pivoted is at the center of gravity of this meter rule, okay, it's a uniform meter rule, then the center of then of course this meter rule is supposed to balance on this knife edge. It's meant to balance on this knife edge, okay, in as much as the meter rule is uniform. But if I decide to apply a little force at one side, okay, you discover that there's going to be a kind of tilting. Now remember there's a distance between the point of the pivot to the point where the force is being applied. So let me call that distance D, and that distance is always perpendicular. Okay? The force is vertical, the distance is horizontal. So the distance is perpendicular. So that is why if I want to evaluate the moment, okay, the moment is going to be equal to force, then multiplied by the perpendicular distance. So always take note of this. Moment is a vector quantity. Why? Because there's a direction between, all right, there's always an angle between the force and the distance, which of course they must be perpendicular. So moment is a vector quantity, and the SI unit of moment is Newton meter. Already you know very well that work have the same formula. Work is force times distance. But the difference between work and moment is that for work, the force and the distance are in the same direction. But moment, the force and the distance must be perpendicular. All right? So the force and the distance must be perpendicular. So that is the difference. Now the question now is, what if I be asked to evaluate the moment of a force if the force is not actually perpendicular to the distance? Okay, let's look at such situation. Still using a beam. Let me still use a beam, okay, or a meter rule. Now, possibly pivoted at a point. Now, a force is being applied. A force is being applied. And it happened that this force that is applied to this beam, please pardon me. It happened that the force that is applied to this beam, okay, is not perpendicular. Let's say a force is applied by tying a rope on the beam, and that rope is making an angle theta. Okay, for a rope has a force on it. The force on the rope is actually tension. Okay, so it's making an angle theta to the horizontal. Now let's look. Say that. Let me shift the pivot. Okay, the pivot. Now the distance from the point of this force to the pivot, let me call it D. Okay. So now, if you are being asked to evaluate such moment, you should know that you cannot, for you to evaluate the moment is not going to be just you multiplying the force, which is the tension, times distance. Why? Because this force is not perpendicular to the distance. Okay. So what will I do to the force? You know what I will do to the tension? Okay. I will have to resolve it vertically. I have to find the vertical component of the tension. So of course, you know how to evaluate the vertical component of a force. So the vertical component of this tension is T sine theta. We've talked about this, okay? So before I can now multiply by the distance. So anytime you discover that the force and the distance are not perpendicular, it is always ideal that you resolve it. Either you resolve the distance or resolve the force so that it will be perpendicular. All right. All right. So now, for example, let's say a situation where the tension here is 20 Newton, which is inclined at an angle of 30 degrees to the horizontal. So you're being asked to evaluate the moment about this pivot. Okay? About the pivot. Simple. If the distance is, let's say, the distance of this, the point where this uh, rope was tied to the beam to the pivot is 2 meters. Let's do that. So this is going to be equal to the tension is 20, then multiply by sine 30. Sine 30, then multiply by the distance, which is 2. So this is going to be equal to 20 times sine 30 is 0.5, then times 2. 0.5 times 20, that's 10. 10 times 2, that's going to be 20 Newton meter. Okay, so I hope that is well understood. Now we can now talk about the principle of moment. Principle of moment. Of course, the principle of moment is the last condition, okay, that I stated, the last condition for coplanar forces to be at equilibrium. Okay, so according to the principle of moment, it said that for a body to be at equilibrium, for a body that is acted upon by a system of forces to be at equilibrium, okay, the algebraic sum of the moment act about a point, algebraic sum of clockwise moment, sum of clockwise moment about the point on that particular body, okay, should be equal to should be equal to equal to the algebraic sum, algebraic sum of anti-clockwise moment. So for equilibrium to be established, okay, what condition for the equilibrium of a body to be established is the algebraic sum of the moment about a point. Of course, the point is that the point where that body is actually pivoted. All right. So the algebraic sum of the moment about a point of turning, all right, should be equal to the algebraic sum of anti-clockwise moment. Now, for this to make sense, I will still illustrate this using our meter rule experiment. So I will actually illustrate the principle of moment using the same meter rule experiment. Okay, so how does that actually work? So I will still balance this meter rule, okay? Make sure that it is balanced at the knife edge by bringing the knife edge to the center of gravity. All right, so now, if this meter rule is balanced, you know very well that, okay, is at equilibrium. But if I decide to now apply a force or add a load at one side, let's say a load of that is at a force F1, all right, you discover that this meter rule will no longer be balanced. Rather, it will tilt to the right. That tilting to the right is a rotation, okay? It will rotate about this pivot in a clockwise direction. So it will rotate in a clockwise direction. So the question is, if I ask you now, if I want this meter rule, even with this weight that is attached to it at one end, to return back to balance, what will I do? All I simply going to do is to attach another weight at the other side. Okay, possibly adjust the position of the weight at this other side. Let me call the weight F2. Then I will now restore the balance. Why is it that by attaching another weight at the other side, I'll restore balance? The reason being that F1 actually produces a clockwise moment. So by the time I actually added F2, it produces a, an anti-clockwise moment. Okay, so I will say that for this beam to be at equilibrium, the clockwise moment must be equal to the anti-clockwise moment. All right, so please take note of that. So that is the principle of moment. Now don't forget that we always, our moment is always about the pivot, okay, or the turning point. So let the distance between this force to the turning point, let it be d2, and that of f1, let the distance be d1. So always make sure that your distance is always about that turning point. So now from what I have, okay, from this beam now I can actually apply the principle of moment. So F1 produces clockwise moment and then F2 produces anti-clockwise moment. So by the principle, we know that clockwise moment is equal to the anti-clockwise moment. Okay, so what's my clockwise moment? My clockwise moment is F1, then multiply by D1, equal to my anti-clockwise moment. What is my anti-clockwise moment? My anti-clockwise moment is F2, then multiply by D2. So clockwise moment is equal to anti-clockwise moment. Okay, let's look at a very typical example. All right, let's see a situation where, okay, a question is reads, a beam is pivoted at the center, a beam of length 100 centimeter. All right, so it's a word problem. As I read, I will actually draw the diagram. So this beam is 100 cm. Please pardon me. So it's a beam of 100 cm. Okay, it's pivoted at the center. So I put the pivot at the center. So what's the center of 100 cm? The center of 100 is 50 cm. So at the center I must represent that 50 cm. So this is the center. Okay, so the question continues. If a weight of 20 Newton is placed 10 cm from one end, so I will just measure 10 cm from one end. Any end will do. So I measure 10 cm. Then I place a weight of 20 Newton. So the question is, at what point from the other end will a weight of 10 Newton be placed to balance it? So at what point at this other end, which I don't know what point it is, okay, will a weight of 10 Newton be placed? So at what point from the other end? So I don't know what distance it is. I'll just call it X. So now you know very well that with what I've set up now, this 10 Newton will go clockwise, will produce clockwise moment, and the 20 Newton produces anti-clockwise moment. All right, okay. And of course, you know, our moment is always we need to get the distance from that particular force to the pivot. So what is the distance from 10 Newton to the midpoint, 50 Newton? Of course, you know that will be 40. From 10 cm to 50 cm, please pardon me. You know that will be 40 cm, okay? Simply that's going to be 50. The center is 50. So this 20 Newton is placed at 10 cm. So that means for me to get the rest of the distance, that's going to be 50 minus 10. Okay, the same happens to this other side. The distance is x. So for me to get the rest of the distance, all I'm just gonna have is 50 minus x. So remember, the whole idea is for me to find x. Okay, so applying the principle of moments, clockwise moment is always going to be equal to anti-clockwise moment. Okay, so clockwise moment is the clockwise moment is 10 Newton, 10 multiplied by the distance, the perpendicular distance, which is 50 minus x. So I'm having 10 open bracket 50 minus x. So it's equal to 20 multiplied by 40. 20 times 40. This is 500. And this is minus 10x. 20 times 40 is 800. Okay, please, I need to make some adjustments so that my answer will not be negative. Okay, so this is, let this weight be 5 Newton. I don't want to have a negative value, okay? All right, just 5 Newton. That's what it is. All right, so just 5 Newton. So I'll just make some adjustment now. So what I'm having here is 5 Newton, okay? So just change that. 5 times 50, I have 250. Then 5x, okay, is equal to, okay, I needed to have, I don't want to have a negative sign. I was supposed to, this is supposed to be increased. Okay, please pardon me. This is 5 Newton. Okay, I made a mistake. This still, the 10, this 10 times, I only changed this, I didn't change this, okay? So 10 times 50 minus x. So what I just changed was what I have here, which I changed it to 5 Newton, okay? So it just 5 times 40. Okay, 10 times this, I still have 500 minus 10x. Okay, so 5 times 40. What do I have? That should be 5 times 40, that should be 200, okay? If I'm not mistaken. So rearranging my equation. So this is going to be 500. 200 comes over. This minus 200. This goes over. That's going to be plus 10x. 500 minus 200 gives me 300. It's equal to 10x. Okay, so x now is going to be equal to 300 divided by 10, which is 30 cm. Okay, so as simple as that. So that is an application of the principle of moments. We're going to look at more application in the next video, okay? See you in the next video. Thank you very much.